Have you ever stared at a complex circuit diagram and just thought, where do I even begin? Well, today we're going to pull back the curtain on a really powerful technique that engineers have up their sleeves. It's called source transformation, and honestly, it's like a secret weapon for simplifying circuits. Okay, take a look at these two circuits. On the left, we've got a voltage source with a resistor in series, and on the right, a current source with a resistor in parallel. They look completely different, right? But here's the wild part. As far as that load resistor is concerned, they are absolutely identical. It gets the exact same voltage and current from both of them. So that begs the question, how? How can two totally different setups produce the exact same result? Well, it's not magic. It's actually a really elegant principle of circuit analysis, and we're going to break it all down. To really get this, we need to start with the fundamental building blocks we're playing with. Let's quickly go over the two types of practical sources. You know, in textbooks, we talk about ideal sources, but in the real world, nothing's perfect. A real voltage source has some internal resistance, which we model as a resistor in series. And a practical current source? Same idea. We model it as an ideal source with a resistor in parallel. These two arrangements are the key to everything we're about to do. And this right here is the core concept. These two configurations are electrically equivalent. That means from the outside, from the perspective of anything you connect to those two terminals, you absolutely cannot tell the difference. They behave identically. So if they're the same, how do we actually convert between them? Let's dive into the Rosetta Stone for this whole process, the transformation rule itself. So what is source transformation? It's really just a method for swapping one of these practical source models for its equivalent twin. It's an incredibly useful trick that lets you rearrange a circuit so you can combine sources and resistors that were otherwise impossible to simplify. And here's the best part. You might think a technique this powerful needs some complex math, right? Nope. The entire thing, this whole elegant process, is built on the very first equation you probably learned in electronics, Ohm's law. V equals I times R. That's it. That's the secret. Okay, let's walk through it. Say you want to go from a voltage source to a current source. It's 3 simple steps. First, you identify your voltage, Vs, and that resistor in series with it, R. Step 2, you just use Ohm's law to find the new current. Is is just Vs divided by R. And finally, step 3, you redraw that part of the circuit, replacing it with your new current source, Is, in parallel with that same resistor, R. Oh, and a little pro tip, make sure the arrow of your new current source points toward where the positive terminal of the voltage source used to be. And, as you probably guess, going the other way is just as easy. To go from a current source to a voltage source, you grab your current, Is, and its parallel resistor, R. Then you whip out Ohm's law again to find the voltage, Vs equals Is times R. Then you just redraw, swapping that parallel combo for your new voltage source, Vs, now in series with the same resistor, R. It's beautifully symmetrical. All right, enough with the theory. Let's get our hands dirty. This is the fun part, where we take a genuinely messy-looking circuit and use this technique to simplify it right before our eyes. So here's our challenge. We've got 2 voltage sources, a current source, and a bunch of resistors all mixed together. Our specific goal is to figure out the voltage across that 8-ohm resistor, way over on the right. Okay, first things first. To simplify this mess, it really helps to have all our sources speaking the same language. Let's convert both of those voltage sources into current sources. For the 120-volt source, we just divide by its 20-ohm resistor. That gives us 6 amps. For the 60-volt source, we divide by its 5-ohm resistor, and we get 12 amps. Just a simple I equals V over R. And look what happens after that one step. Suddenly, our circuit is so much cleaner. We now have 3 current sources and 3 resistors, and they're all sitting nicely in parallel with each other. This is way easier to work with. Now that everything's in parallel, we can start combining things. For the current sources, we can just add them up, but we have to be careful with the direction. That 12-amp source is pointing down, fighting the other 2. So we've got 6 amps minus 12 amps plus 36 amps, which gives us a total of 30 amps. For the resistors, we just use the parallel resistance formula, and those 3 combine down into a single 2.4 ohm resistor. Will you look at that? That entire complicated network has now been boiled down to just one 30-amp current source in parallel with a single 2.4 ohm resistor. This is so much simpler. And to make our final calculation even easier, let's do one last transformation and turn this back into a voltage source. So, one last time with Ohm's law. We're looking for voltage, so V equals I times R. Our equivalent voltage is 30 amps times 2.4 ohms, which works out to 72 volts. This new voltage source will be in series with that 2.4 ohm resistor. And this just shows you the incredible power of this technique. That original, complicated beast of a circuit is now this beautiful, simple, single-loop series circuit. This is something we can solve in our sleep. It's just a basic voltage divider now. So to find our answer, we just use the voltage divider rule. The voltage across our target 8-ohm resistor is going to be its resistance divided by the total resistance in the loop, all multiplied by our 72-volt source. You run the numbers, and there's our answer. 48 volts. We did it. By just repeatedly applying one simple rule, we were able to solve a problem that would have been a whole lot messier with any other method. So you might be thinking, okay, that's a cool trick, but why does this really matter? Let's talk about why this is more than just a neat party trick. It's a genuine superpower for your circuit analysis toolbox. Well, for starters, it turns those intimidating multi-source circuits into something manageable. It lets you combine parts of a circuit that looked completely stuck. It can make more advanced techniques like mesh or nodal analysis way, way easier to set up. And the best part? It's all just a clever, practical application of Ohm's law. At the end of the day, the idea is really intuitive. Think about it like this. A light bulb doesn't know or care how it's being powered. As long as it gets the voltage and current it needs, it's going to light up exactly the same. From the bulb's perspective, the original source and the transform source are completely indistinguishable. That's the whole idea of equivalence. And that kind of leaves you with a bigger thought, doesn't it? If a complex electrical circuit can have a much simpler equivalent version hiding inside it, what other complex systems, maybe in technology or nature or even society, might also have simpler equivalent forms that we just haven't figured out how to see yet?